Let's first try solving this with the formula method. Now it is clear that the general term for this series can be written as nCr divided by r plus 1, and since there is an alternate plus minus sign, I need to add a minus 1 to the power r as well. So if I sum this from r going from 0 to n, I get my series. Now I'll use the formula that we just saw earlier, n plus 1 cr plus 1 divided by n plus 1 equals nCr divided by r plus 1. Plugging in the value here, I get 1 upon n plus 1 summation minus 1 to the power r, n plus 1 c r plus 1. I can expand this summation further to get n plus 1 c1 minus n plus 1 c2 plus n plus 1 c3 and so on until n plus 1 c n plus 1. Now I can add and subtract n plus 1 c0 to this expression. I know that this sum amounts to 0, as we have already seen earlier. Minus 1 to the power r cr going from 0 to n goes to 0. So minus 1 to the power r n plus 1 cr going from 0 to n plus 1 will also amount to 0. And n plus 1 c0 is 1. So my answer becomes 1 upon n plus 1. So option 4 is the correct answer. Let's try to solve the same thing using the calculus method. This time I'll start with the series 1 minus x to the power n, since I need to get alternate plus minus signs. Again, I'll integrate with respect to x with ranges going from 0 to 1. On my left hand side, I get minus 1 minus x to the power n plus 1 divided by n plus 1. On the right hand side, I get c0 x minus c1 x square by 2 plus c2 x cube by 3 and so on with my limits 0 to 1. Putting in these limits, I get 1 upon n plus 1 equals c0 minus c1 by 2 plus c2 by 3 and so on until minus 1 to the power n cn upon n plus 1. Hence, my desired sum is again 1 upon n plus 1. So option 4 is the correct answer.